Percent elongation is defined as the measure of the difference between the final gauge length and the original gauge length divided by the original length of the specimen. This is a measure of strain and can determine if the body is ductile or brittle. Meaning to say, if you have a percent elongation greater or has a large number of percent elongation, meaning to say the body is more ductile, meaning it can stretch more before it will break. But if you have a small percentage elongation, meaning the gauge length or the specimen broke at a smaller length, meaning that specimen is brittle. So it determines the ductility of the specimen. So to illustrate that, this is the original gauge length, L sub O for example. Then this may be the change in length. Call that as delta L. Then this entire length you see here is the final gauge length, or L sub F or LF. So that's how this percent elongation looks like when you test the specimen. So about the percent reduction of area. So the reduction area happens during the elongation of a body wherein the cross-section of the specimen gradually becomes smaller. The percentage reduction in area measures that. So in mathematical terms, it is the original area minus the final area over the original area. So what happens when you pull a specimen out? It gradually decreases in area. So that's what happens. So this is an exaggerated figure. So at this point, there's a reduction in area happening. So maybe this is the original area, A sub O, and then this is the final area, A sub F. So you measure the difference between the two. The tensile strength measures the load it takes to break the specimen. It is a simple measure of force over area. So if we're familiar with pressure, it is synonymous to pressure. So this UTS is the ultimate tensile strength. So this ultimate tensile strength measures the strength of the material at its breaking point. That's why the Pmax here is the load to break the specimen, and the area is the specimen's original cross-sectional area. So to illustrate that, the cross-sectional area is the cross-section normal or perpendicular to the force. For example here, if you have a specimen, a pipe, then you pull that pipe in this direction. This is the normal force or perpendicular force to the area of the pipe. So that's how you measure the cross-section of the specimen. So it should be perpendicular to the cross-section. The force should be perpendicular to the cross-section. So for example, you have a force here of 10,000 pounds. You just divide it by the area here. So if you have an area of a circle here, you just utilize the formula earlier, pi times r squared, or pi over 4 times d squared, where r is the radius and d is the diameter. Then you divide those two, the result of those two. So this formula applies the UTS formula for a full section of a pipe. So the formula you see here is the Pmax is just the load in pounds or in Newton for SI unit. The 0.7854 you see here is the one that I mentioned earlier, which is pi divided by 4. The OD is the outside diameter of the pipe. Then the ID is the inside diameter. You can write that formula as well as UTS is equal to Pmax over pi over or 4 times OD squared minus ID squared. Later, I have an example showing this formula and how to use them. Next is the yield strength. Yield strength is measured by the load applied at the offset divided by this original area. The offset is the arbitrary point of the material's elastic limit, and when exceeded, the material will no longer return to its original condition. So the yield strength of a material is defined as the offset, load at the offset, meaning the force at the offset here, say for example, this is the offset, this is the yield point, this is the proportional limit, and this is the elastic limit. This is the stress and strain curve, if you're familiar with that. So after reaching this yield point, the material will no longer return to its original position. So for example, you pull a force here, then it reaches beyond the yield point, it will no longer revert back to its original position. For example, this is the point of the original position of the bar or the specimen. So if you exceed the yield point, it will no longer return to this original position, meaning this is the deformation. So the cross-sectional area you will use there will depend upon the specimen. So if, for example, that is a rectangle, you will use the width times the thickness. So if it is a bar, you will use the diameter or the area of a circle. So for the calculation of ultimate tensile strength, so we have an example here. Calculate the ultimate tensile strength in megapascal of a tensile specimen having a cross-sectional area of 0.3 square inch and broke at a tensile load of 24,600 pounds. So if you can remember the formula of ultimate tensile strength, which is the force maximum or Pmax divided by the original cross-section, which is the, in this example, the 0.3 square inch. So 24,600 pounds divided by 0.3 square inch. So that will give you a value of 82,000 pounds per square inch or PSI. So how about we use that example to calculate the ultimate tensile strength of the pipe? So if you may remember, the formula of UTS or the ultimate tensile strength of the pipe is Pmax over its cross-sectional area, which is 0.7854 times OD squared minus ID squared. So this is just the maximum force over the diameter of the or the cross-section of the pipe, which is pi over 4 times its outside diameter minus squared minus the inside diameter squared, because as you can see, the pipe has a hollow cross-section, meaning the inside diameter is hollow and you have a thickness here or the outside diameter here with a certain thickness, so that you will utilize that thickness in this equation as well. So the given here is the maximum force Pmax is 5,000 pounds. The OD is 10.75 inches and the pipe thickness is 0.375 inch. So how will we get the internal diameter first, because we don't have the internal diameter? So drawing the cross section of the pipe, so we have the OD here and the ID here. So the dimensions we have here is that we have the OD as 10.75 inch, and this is the thickness, which is exaggeratedly 0.375 inch. So we can get the internal diameter by subtracting the OD to the twice of the thickness of the pipe, because you can measure the thickness as well on the other side, 0.375 inch, and this is now the internal diameter. So you multiply that by twice the thickness, or subtract that by twice the thickness. So ID is now 10.75 inch minus 2 times 0.375 inch. So that will give you 10 inch as your internal diameter. So going back to that formula, so UTS is now 5,000 pounds over 0.7854 times 10.75 squared minus 10 squared. So the unit of this one of the denominator is inch squared, because you square both of the dimensions in the denominator. So this will give you a value of 409.1 pounds per square inch. So that will be the ultimate tensile strength value of the specimen. So how do you calculate now the percent elongation of a bar with original length of 150 mm and it is stretched to 152.5 mm? So if you can remember, the formula of percent elongation is that it is the final length minus the original length all over original length. Multiply this expression by 100%. You get the percent elongation. So 152.5 mm minus 150 mm, divide that answer of that expression to 150 mm times 100%. So this will give you 152.5 minus 150 is 2.5 mm divided by 150 mm, multiply that by 100%. So this will give you a percent elongation of 1.67%. So that is the answer. So how do you know if a material passed the percent elongation or not? So that depends on the standard the material is governing with. So if it, for example, it is being governed by ASTM standard, ISO standard, so it has an acceptable percent elongation for which the material is acceptable to be stretched to at some point. So if it is stretched at a percent elongation lowered at some value, so it will not be acceptable because the material is brittle. So it doesn't have enough ductility to basically survive the force that it will be subjected with. So for the percentage reduction in area, so we have the original area of 2.5 square inch reduced to a final area of 2.15 square inch. So percentage reduction in area is given by the final area minus the original area all over the original area times 100%. So the final area here is 2.15 square inch minus the original area 2.5 square inch all over 2.5 square inch times 100%. So never mind the negative value that you'll receive here because it is a reduction. So meaning a reduction will automatically give you a negative value. So 2.15 minus 2.5 over 2.5. So that is times 100%, that is 14% reduction in area.